Okay, so we're moving on to another topic. Um, yeah, so actually everything we've done, this linear programming stuff, so that's like your second assignment, basically that's the second chapter in the notes, and then now we're on like the third thing. I think this is a topic that's familiar to a lot of people. If you've taken graph theory, then it's going to be familiar. Even if it isn't, don't worry, because we're going to build everything up from scratch. But even if it is familiar to you, I hope that I'll be able to give you a sort of different perspective on matchings and flows. Actually, this is the time in the course where I think things get quite interesting, because the whole time from now on, I'm going to present these topics, which are supposedly new topics, but then we're going to see like all of these kind of interesting connections that go back to all of the other topics. So, this is going to connect to linear programming. So I'll talk about matchings, then we'll talk about flows, which is going to connect back to matchings, and also linear programming, and everything is going to be kind of interconnected. So yeah, I think all these connections are quite interesting. So yeah, in case you're not sure what a matching is, let me define it. So a matching in a graph G is a set M. I think I already defined this earlier in the course also, but here's just a refresher. So it's a set of edges with the property that no vertex is in two edges of M. Or in other words, no two edges in M share an endpoint. So such that no two edges in M share an endpoint. Endpoint is just like the vertex at one of its ends, right? So if this is a graph, then if I color these edges red, so these red edges would form a matching. If I had, if I add this edge, then okay, these two edges share an endpoint. This is not a matching now, right? Okay. How many people know this concept already fairly well? Okay, most people. Cool. So it'll be some review, but then some new stuff as well. Okay, so let's define. So usually with matchings, we're interested in finding the biggest matching. So definition, let new. So new looks kind of like a kind of curly V, right? Nu of G be the maximum cardinality of a matching, so it's the maximum of the cardinality of M, such that M is a matching in G. Okay. Okay, so then there's this closely related concept of a vertex cover. I know I already defined this as well, but we didn't really go into it deeply. So a vertex cover is a set, let's say C, of vertices of the graph. So let G be a graph, there's some graph here. So it's a set of vertices such that every edge has at least one endpoint in C. So every edge of G has at least one endpoint in C. Okay. Okay. So another kind of interesting problem is to compute the size of the smallest vertex cover. So like a vertex cover, you're trying to pick vertices kind of strategically to hit all the edges. Like every edge has to get hit at least once, meaning one of its endpoints has to be in the set. So I'm trying to like hit all the edges and have as few vertices as possible. So I don't know. I haven't thought about this graph in advance, but like, okay, I need to hit these edges. I might pick that vertex, right? I don't know, what's a good idea? Probably high degree vertices are a good idea. Let's take that one. I gotta hit that edge. It'd be stupid to pick that one, right? That only hits one edge, so I may as well pick that one. I'm missing this edge and this edge right now, and that one. It's a little bit awkward. Maybe I'll take that one, and now I'm missing this edge, so I gotta take another one. So I don't know. That's a vertex cover of size 4. Maybe there's one of size 3, but I kind of doubt it. Probably 4 is the best. Okay, so yeah, we've got this. So another parameter of a graph. So tau of G is the minimum cardinality of a vertex cover. So it's the smallest C, the minimum C, such that C is a vertex cover in G. Okay. Any questions about this so far? Okay. So there's this, I tried to explain this maybe near the beginning of the course, but I'll remind you of this again. This idea that, you know, in some sense, these problems, the problem of computing nu of G and tau of G, okay, they're, in some sense, they satisfy some kind of a weak duality condition or constraint that nu of G is always at most tau of G for every graph G. Okay. And you should think of this like duality, like linear programming duality, right? We had when you have a maximization problem for a linear program, the dual is a minimization problem, and they kind of meet in the middle or something. This one, okay, this is an inequality, not an equality, but it's the same kind of idea. If I want to maximize, you can get an upper bound on the matching, so this is called the matching number. So nu of G is the matching number. This is the vertex cover number. But basically, this gives you an upper bound on this. And the proof of this is it's just pigeonhole, basically. So let M be a matching and C be a vertex cover. So, yeah, how do you kind of argue this? Like the thing is, if M was bigger than this vertex cover, the vertices of C hit every single edge in the graph. In particular, the vertices of C hit every matching edge, every edge of M, right? So yeah, how do I kind of say this? So for every edge in the matching, one of the endpoints, at least one endpoint of E is in C. Okay. And also no vertex of C is in more than one edge of M, right? Because actually no vertex in the whole graph is in more than one edge of M, right? The endpoints of the things in the matching are different vertices. Anyway, if you put these two things together, if you think about it, that does, kind of imply that M is going to be at most C. Because, yeah, you could go through each, edge of the matching, count how many of its endpoints are in C. That will count every vertex of C at most once. And then anyway, it'll give you this inequality. Anyway, you could also see this by pigeonhole. You're like, you take your C, imagine M was bigger, then there'd be two matching edges, hitting the same vertex, but that'd be a contradiction. So, I mean, there's different ways to argue this, but this is supposed to be the easy part, right? But any questions about that? Okay. Actually, here's an observation. This vertex cover number, it's actually, computing the vertex cover number of a graph is pretty much the same thing as computing the biggest stable set or biggest independent set. So here's a very simple observation. Oh, maybe I'll give you a definition that, so let's say alpha of G is the maximum cardinality of a stable set. So it's biggest S, such that S is a stable set in G, or, I mean, other terminology that might be more familiar is independent set, right? So yeah, if I take a kind of simple observation is that if C is a vertex cover if and only if the complement of C is a stable set. Okay. Maybe it's worth thinking about this, right? Can anyone see why this is the case?
If two vertices in complement of C and they are not those sets, means there is one edge between these two sets. So in C, this edge is not covered by any vertex.
Yep, exactly. Yeah, right. And that's like one direction, but both directions are the same basically. If there was an edge, so just to say again, like if there were an edge between two vertices in the complement, then well, those are two vertices. That's an edge for which neither endpoint is in C, so then it's not a vertex cover, right? And vice versa, if you know, if there are no edges in here, then it would be a vertex cover because it hits every edge. Okay, so actually really this whole, if you know what the independence number, so this is the independence number alpha, if you know what that is, I mean this tau is actually nothing, it's not like really a new concept. It's just going to be equal to the number of vertices in the graph. Minus the independence number or stability number or whatever we're calling it in this course. Right, so this is just by that observation. But here's something interesting. So we're sort of going to, well, we're not going to see this in full generality, but we're going to somewhat see that, well, it turns out that computing the biggest matching in a graph is polynomial time solvable. Okay, we won't actually see the full algorithm for that, but we'll see some algorithms in special cases. But computing the independence number is hard. Actually, you kind of, if you did the first assignment, you kind of did that in a sense. Remember, you proved that the stable set problem is NP complete. That implies that computing this number is NP hard. So like what we've got here is we've got something that can be computed in polynomial time, and this is like computing this is NP hard, and they're sort of like got this kind of dual relationship. Okay. So an interesting thing is, though, that if you restrict to bipartite graphs, this problem is not hard anymore. In fact, these two things just end up being equal. Okay, so that's the first thing we're going to prove. Oh, I need some more definitions before we can prove that, though. Okay, so I want these. So yeah, a few definitions. So say that, so let G be a graph and M be a matching in the graph. So we say that a vertex V is M saturated. So all this is going to mean is that there's an edge of M that has V as an endpoint. So if there exists an edge in M containing V, okay. So in other words, if we're trying to make a largest matching, we're trying to make a matching that saturates as many vertices as possible. Another kind of key definition is something called an alternating path. So again, G is a graph and M is a matching. A path in G is M alternating if the edges of the path kind of alternate between being in the matching and not in the matching. So the edges alternate, so the edges of the path between being in M or not in M. Okay, and it doesn't matter which one comes first. Like it could be M, not M, M, not M, or it could be not M, M, you know. It just has to alternate. So, you know, if my red edges are the matching, yeah, this would be like an alternating path. But yeah, it could also start with M, then become not M, then M again, right? So like these alternating paths are kind of, it's like they're kind of surprisingly important. Like it turns out, basically if you want to increase the size of a matching, you should find like an alternating path that will allow you to increase the size by kind of switching the edges along the path. So specifically, so there's a special name for like an alternating path where you can switch the edges on the path from being in M or not in M. So that's called an augmenting path. So an augmenting path, so an M augmenting path the word augmenting just means make it bigger, kind of, I think. Like if you augment something, you just make it, you add to it. So that's what's being conveyed here. So an M augmenting path is an alternating path. So an M alternating path whose endpoints so the first vertex and the last vertex of the path are not M saturated. So yeah, the idea here is, I've already lost my red chalk. You've got, oh, here it is. Right, if you imagine you've got a path that goes from not in the matching, blah, 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 and the endpoints are not in any matching edges at all, then you could just, because like this thing's not saturated, so I could just put that edge in the matching, take that one out, put that one in, take that one out, put that one in, take that one out, put that one in, and now I've gone from 3 edges here to 4 edges, and it got bigger, right? So that's the kind of idea of an augmenting path. Any questions about that? Yeah. Yeah, that's right. So it's saying, yeah, first of all, it's alternating, and you're saying that this one's not and this one's not saturated. So there's, you know, if you go one step further, no matter which neighbor you look, like there are no matching edges here or here, and then if you do that switching, now these will become saturated by like the first and the last arc, or sorry, edge, I mean. Yeah. Like if this one was saturated, then yeah, you can't really flip the edges, right? Because you'll put that, you'll put that one into the matching, and then it won't be a matching anymore.
Could you reset any of those endpoint edges?
Well, like I can't, with this current matching, I can't just like, oh, I see what you mean. No, because actually I don't know if there are other matching edges sitting over here somewhere. Oh. So yeah, you would love to just like throw one of these in, but you can't do it, yeah. Yeah, because the other endpoint may have a problem. Yeah. Any other questions? Here's the thing that I find surprising about matchings is that, so suppose you want to find the biggest matching. Suppose you found a matching and you want to make it bigger. You might think that there might be like lots of strategies to make it bigger. Maybe you have to like just change a whole bunch of things or whatever and get a bigger matching. But actually this is finding an augmenting path is like the only way. I mean, in some sense, if you can make it bigger, then there's an augmenting path. If you can't make it bigger, then there's not an augmenting path. This is the key to making a matching bigger. So, of course, finding an augmenting path is not necessarily trivial. But this is a lemma. Exactly, yeah, yeah. So the augmenting paths completely determine when you've got the biggest matching. Yeah. That's exactly the statement of what I'm going to prove right now. So, yeah, so let M be a matching in G. So then, we can write it like this. The size of M is equal to nu of G, meaning it's the biggest, it's one of the, it has maximum size if and only if there doesn't exist an M augmenting path. So note that if you, like, this seems kind of interesting. It's kind of surprising that it's so simple, just a simple condition. It doesn't really give you an algorithm, though, because it's like, okay, so I've got a matching. What can I do to, like, do I have to try all the possible paths? There's a lot of paths in a graph, if you think about it. So, yeah, this doesn't really give you an algorithm, but it does give you a very simple condition. Either there's an augmenting path or there isn't, right? I guess it kind of shows that determining if this is true, like if the size of M is equal to nu of G, is in co-MP or something, because it's like, if the answer is no, that's my certificate, right? Okay. Okay, so here's the proof. One direction's easy. If there is an augmenting path, we just do what I said over there and switch the edges on the path, and it'll get bigger. So if there is an augmenting path, we just switch the edges. So meaning they switch from being out of M to in M and in M to out of M. On the path, and get a bigger matching. Okay, so that proves that if this statement is false, then this one is false. Like, so I'm kind of proving the contrapositive of both directions. So what I'm going to prove now is that if M is smaller than nu of G, then there is an augmenting path. So now suppose size of M is less than nu of G. Okay, and our goal is to find an augmenting path. So yeah, there's a simple trick for this. Well, okay, M is smaller than nu of G, so there is some matching that's bigger than M. Let's look at that matching. So let's take a matching, so of the maximum size. So let M prime be a matching like with cardinality equal to nu of G. Okay, so it's bigger than M. Okay. So take a graph. So take the subgraph of of G with vertex set, so same vertex set, V of G, and edge set. So it's going to be the symmetric difference of M and M prime, meaning it's like M minus M prime union M prime take away M. So in other words, it's the symmetric difference. Or if you took Math 122 here at UVic, I think this is an unusual notation for this, but I think that's what you might have seen, right? I don't know. Oh, a square thing would be like a disjoint union. So it's not that though. Well, I mean, in some sense, this is a disjoint union because these sets are disjoint. So you could put a square bracket there if you wanted, but usually the square bracket is conveying the fact that you're taking a union and the sets are disjoint or something. But yeah, anyway, it's this set. Take the things that are in M and not in M prime, and the things that are in M prime and not in M. And it's helpful to think of these edges as colored. So let's color these edges red. And color these ones blue. Okay. And since these are matchings, like every vertex has at most one red edge touching it, and at most one blue. That actually makes the graph fairly simple. Like, you know, it turns out if you have a graph, right, where every vertex is degree 0, 1, or 2, the graph is just a bunch of like cycles and paths. So, yeah, so this graph looks basically like, so you might have some components where everybody in that component has one red neighbor, one blue neighbor, right? You also will have things, I mean, you could just have some edges just sitting out, like that, maybe an edge like that. You could have like, also like these kinds of paths, right? Okay. So all I'm trying to say is every component, every vertex has at most one red edge and at most one blue. So each component's either going to be like an even cycle where it alternates red, blue, red, blue, red, blue, or it's going to be a path where it alternates, again, like red, blue, red, blue, red, blue. And this, I consider this to be a path as well. Oh, and then you've got some like, vertices that are not involved in anything, for example, like, but yeah. Okay. So I claim that you can't have all of the components looking like this. They can't all be cycles. Can you see why?
Let's say the number of edges from each matching.
Yeah, exactly. If I look through each cycle contributes, like this one has 3 red edges, 3 blue edges. If it's generally, you're always going to get the same number of red and blue in every cycle. But we just know that there are more blue than red, right? Because this, I mean, yeah. The symmetric difference, like, since M prime has more things than M, there are just more things in here than there are in here. So there are more blue edges than red. So one of the components has to be a path that starts with a blue edge and ends with a blue edge. Oh yeah, there could be paths. I don't think I drew any, but you could have paths that have the same number of each. So like generally there has to be at least one component that is a path with more blue than red, right? And that's our augmenting path. So maybe I won't write all the details, but let's kind of convince ourselves of this. So like if I have this component, I think it's clear that this is an alternating path, right? Because what does a blue edge mean? It means it's in M prime, not M. So this first edge is not in M, then that's in M, not in M, in M, not in M. So it's alternating for sure. What I also need is that the endpoints are not saturated in like M, right? So if you think about it, okay, if I look at that vertex, I don't see any red edges. So there are no edges from M minus M prime incident to that vertex. The only other edge of M that could be incident to that vertex is one that's in M and M prime. But that can't be there because M prime is matching and there's a blue edge already. I'm not sure if that makes any sense. So I'm trying to say if I look back at the matching M, there are no edges of M touching that vertex. There are no red edges there, so those ones are not touching that vertex. The only other edges of M are the ones that are in M and M prime, which are not present in this graph, right? But there couldn't be one of those edges because then this vertex would have two edges that are in M prime, but it's a matching. And so that doesn't happen. So basically, so there exists a component which is a path with more blue than red edges, so which starts and ends on a blue edge. So this is an M augmenting path. Any questions or, I don't know, anyone want to protest that proof? I don't know, like is that enough detail or does that, okay. All right, if you went through this again, you would be able to reason out all of these things. Like it's definitely alternating and you just have to check that the endpoints aren't saturated by M and they're not, so. Okay, so that tells us that like if you want to get a bigger matching, find an M augmenting path. That's like the only way to do it. Or maybe that's not the only way to do it, but that's like always a way that will work, right? Okay. All right, so the next thing I want to prove is König's theorem. So what this says is if G is bipartite, then the matching number of G is actually equal to the vertex cover number of G. Okay, So we had this relationship before that there was an inequality, but actually if it's bipartite, magically these things just end up being the same thing. Okay. And in particular, it's kind of interesting that when so if it's a bipartite graph, we're going to also show soon that you can compute this number in polynomial time. And so therefore, this one can be computed in polynomial time. Therefore, you can solve like the stable set problem, for example, in polynomial time. Because, yeah. Okay. So, all right. So we already know that nu of g is at most tau of g. So we just want to show it's equal. So we want to show that tau of g is at most nu of g. Okay. What I'm going to do is I'm going to pick a maximum matching. And then I'm going to show that I can find a vertex cover of cardinality at most the size of the matching. So let M be a maximum matching. And our goal is to find a vertex cover C with cardinality at most the cardinality of M. Okay, and then tau of G is the minimum vertex cover, so the minimum would also be, Okay. All right, so we're going to need to kind of think of the two sides of the bipartite graph kind of separately. So let's let xy be the bipartition of G. So all the edges go from x to y, Okay, and some of these edges are in the matching and some of them aren't, right? So what I'm going to try to do, so we know that this is a maximum matching, so there aren't any augmenting paths. What I'm going to do is like try to make an augmenting path somehow, and it must fail, and then somehow use that to get my set C. Well, okay, the way I'm going to present it is a bit different. I'm going to define the C, and then we're going to show that because there are no augmenting paths, this is actually a vertex cover. So here's how it's defined. So let U be the M unsaturated. So unsaturated just means not saturated. Vertices of X. So vertices in X. Okay. It could be empty, I don't know. But I should say set of, right? And I'm going to define a set to be like some set W, which is all of the things I can reach from an alternating path that starts in U. So I start with my U and look at all of the alternating paths, and let's find every vertex that I can reach with an alternating path. So let W be the set of vertices that can be reached by an M alternating path starting in the set U. Okay. So this is really just, this is trying to build an augmenting path, which I know can't exist, but if it does exist, I get some kind of contradiction, right? Because like, remember, an alternating path has to start at an unsaturated vertex. And yeah, I'm basically trying to, yeah, to also end at an unsaturated vertex or something. So, you know, by the way, if you start at U, at some vertex in U, right, this vertex is not saturated. So if I take an alternating path, the first edge is always not in the matching because it has no matching edges touching it, right? The second one is always in the matching. Which means that actually, like so I'm always crossing back and forth on the bipartition. Whenever I cross back to this side, I'm actually at a vertex that is saturated because literally that edge made it saturated, right? And then I cross over here. And this one, if it's not saturated, I could find a bigger matching. So it must be saturated, so I could like, anyway, so this is, so basically I'm starting over here and I'm trying to find, if I reach an unsaturated vertex over here, I've got a contradiction, right? Okay, so now I'm going to define the vertex cover. It's not going to be clear why it has the right properties, but then we'll show it does. So I'm going to define C to be all of the things that are in X, so that like the left side of this bipartite graph, but are not in W, union the things that are in Y and are in W. Okay. Completely not clear why this is a good choice, but it turns out it's going to work. So what I need to show is firstly that C is a vertex cover. And I need that C, the size of C is at most M, the size of M. It's actually going to be equal, but yeah. Okay. All right, maybe I can get rid of this stuff. So suppose, so let's prove it's a vertex cover. Suppose it's not. Let's do it by contradiction. So suppose C is not a vertex cover. Okay. Well, what that means is that there's some edge that doesn't get hit by C. But that can only happen in a quite a specific way. Like, you know, I've got my set X, which is divided into like X minus W and X intersect W. And I've got my set Y, which is like Y intersect W and Y minus W. And like, my set C is this stuff and this stuff, right? So this is like, you know, these things are the set C. So if there's a edge that didn't get hit, it must start here and end here, right? Because if it had an endpoint here, I've hit it. If it had an endpoint here, I've hit it with that stuff. So then what this means is that G has an edge from x intersect W to y take away W. Can anyone see how this is going to be a contradiction? Let's say I call this vertex here, I don't know, x and this one y. Let's say, so x, y. Yeah, why can't this edge exist? Yeah. Oh, yeah.
Because the edge would be an M alternating path?
Yeah, exactly. I mean, because, yeah, basically, like, there's some, because this is in W, there's some alternating path that can get to this x, right? Actually, as we observed, the first edge of the alternating path is always not in M. Okay, actually, sorry, I shouldn't be pointing here. The first edge starts in U, and so it's not in M. The second edge is in M, blah, blah, blah. So when the alternating path like entered this vertex, it was a matching edge. And this one is, so then therefore this one is not a matching edge because matchings don't have any edges the edges don't have endpoints in common. But then, yeah, you could just say, add on that edge, and it'll be an alternating path that ends here. Yeah. Unless this thing appeared earlier on that alternating path, then I've repeated a vertex. But if it appears earlier on the alternating path, it's also on an alternating path. Yeah, so yeah, this would be a contradiction. So this can't happen. Because x is in an alternating path. If y was also on that alternating path, then y would be in W. So if y appears on the path, then it is in W, which would be a contradiction. If it doesn't appear on the path, like I'm talking about the path that ends at x, right? Then if I add the edge x, y to the end of that path, it makes a longer alternating path that actually does end at y. And again, that contradicts the fact that y is not in W. So adding x, y to the path gives us an alternating path that includes y. But that, again, contradicts the fact that y is not in, W, right? You do have to be a little bit careful because it is important that, like, I know that the edge that comes into x, if there is one, on that alternating path was a matching edge, and then the next one won't be. Like, if it was not a matching edge, and then I added this one, if it's also not a matching edge, then that wouldn't be a alternating path, right? But I know that when I take an alternating path that starts on the left side, every second edge is a matching edge. So yeah. So then this one's not in the matching, and therefore it's an alternating path. It's a little bit of a subtle detail there, but yeah. That's also fine, because the whole thing I'm doing here is proving it's a vertex cover. If that set's empty, that just means, like, all I'm trying to prove is that there can't be any edges from here to here. If this is empty, then that's already true. Yeah. That's a good question, yeah. Yeah, I'm proving there's no edges here, and therefore every edge must hit this set or this set. Okay, any questions about that? Okay, so it is it is a vertex cover. Let's prove that it has the right size. Okay, so note that because M is a matching, each vertex in C is contained in at most one edge of M, right? I mean, this actually has nothing to do with C. Every vertex in the whole graph is in at most one edge. That's what it means to be a matching. What we want to show is actually kind of a opposite version of that. I want to show every matching edge has exactly one vertex of C in it. So we show that every edge in M has exactly one endpoint in C. I also want to show, I want to show two things. Let's call this like 1 and 2. I want to show every edge has exactly one endpoint in C. And secondly, I want to show that every vertex of C is in exactly one edge of M. Okay. If these two things hold, so I already know that it's in at most one edge of M, but I need it to be exact. If these two things hold, then there's an easy like bijection between M and C. Right? Each matching edge, I could map it to the unique vertex, the unique endpoint that's in C, and each vertex of C, I could map it to the unique edge M. Yeah, so this will imply that they have the same size. Right, because there's like this one-to-one correspondence between M and C, if I can prove these things are true. Okay, does that make sense? Okay. Well, actually, maybe I want this drawing again. Like, so for the first statement, so the first statement can only go wrong if there's an edge of the matching that goes like this. So I'm trying to prove that every matching edge So every matching edge I know already has at least one thing in C because C is a vertex cover. But the only way this can go wrong is if there are two things that are in C. So suppose there exists an edge in M from x minus W to y intersect W. Again, I want to get a contradiction from that. Okay. Can I even see how this is going to work? Yeah.
Basically, all the vertices in x minus w are unsaturated, but all vertices in y intersect w are all unsaturated, so there cannot be any contribution.
I don't know if I know whether these things are saturated or unsaturated. I mean, what I know is that there's I think maybe the argument is this, like there's an alternating path that starts at U and ends here. The last edge of that must have been not in the matching, because that's how it goes. It goes like not in the matching, in the matching, not in the matching, in the matching. The last one was not in the matching, but then that's going to give me like an alternating path that goes to here. So just by following the next thing there, right? So I think this, so this can't exist, I think, because, so it can't exist because we would get an M alternating path to x minus W, but that's, by definition, there are no such paths, right? Because I would just take an M alternating path that ends here, and then add on one more edge. Okay, so that kills, so that proves the first statement. Now I want to show that every vertex in C is in exactly one edge of M, so it's not in 0. Actually, up until this point, I haven't used that this is a maximum matching. So this is where it's going to come into play. So suppose, so this is to prove the second statement now. So suppose there's a vertex of C that's not in any matching edge. Well, I guess let's think about, is it, could it be an X? So one thing was a kind of subtle point I haven't said, I mean, I haven't kind of explained yet is, remember we started with this set U of the unsaturated vertices, and then I defined W? Well, maybe, I mean, hopefully it's clear that U is a subset of W because U is the things that are unsaturated in X, and then W is the things you can reach from U with alternating paths. If I take an alternating path of length 0, from U, I just get the vertex of U. So this is a subset of that. So like the vertices of U, they kind of live up here. And so like if it cannot be the case that any of these vertices are unsaturated, because the unsaturated vertices are here. They're in W. So this can't happen. So no, you can't have a unsaturated vertex of the of C that's in X because U is a subset of W, and like C. Remember, C is like X minus W union Y intersect W. So the things in X that are in C are the ones that are not in W, right? Okay. Now the question is, could there be a vertex of C that's in Y and is not saturated? So let's say that vertex is not saturated. So why or why not? So there can't be a vertex here that's not saturated because I know that I can start at an unsaturated vertex of X, take an alternating path that ends here. If that wasn't saturated, that alternating path would be an augmenting path because it starts at an unsaturated vertex and ends at an unsaturated vertex. So that's no, because we would get an alternating path, or sorry, an augmenting path. Okay, so this proves that, C has the same size as M, and it's a vertex cover, so it is, So therefore, the König's theorem is true. A little bit of actually kind of a convoluted proof, but yeah, I think the key idea is like the super clever thing is come up with this definition of W and then just write down the C and then just think about it like and work out that it has the same size as M and it's a vertex cover. Okay, any questions about that? Okay. I think I'll maybe just give you some definitions and stuff and state some theorems, and then that'll be all for today. So so you may have heard of a perfect matching before. So a perfect matching in G is a matching in which every vertex is saturated. Okay. In bipartite graphs, the famous kind of theorem about perfect matchings is Hall's theorem. So on one of your assignments, you'll have to prove Hall's theorem using König's theorem. It's a very standard thing. So let G be a bipartite graph. With bipartition XY. So then there exists a matching that saturates X if and only if, so I'm not sure if I've introduced this notation or not, but if I haven't, then I'm going to do it in a second. The size of the neighborhood of S is at least the size of S for all S, which is a subset of X. So in particular, so this is just talking about a matching that saturates X, but if X and Y had the same size, then this would be a perfect matching. So in case I haven't done it yet, let me just say that this notation, so for a vertex V, or let's say U, so N of U is the set of all V such that UV is an edge. This is called like the neighborhood of V. And then if I have a set of vertices, I don't know, I think there can be different, in the setting of a bipartite graph, it's not going to matter, but maybe there could be different, anyway, I'm just going to say it's the union over all V and S, or let's say U and S, of the neighborhood of U. So this is for a set of vertices. Okay. So what Hall's theorem basically says is that either there's a matching that saturates X unless there's some kind of obvious bottleneck that would prevent that. What I mean by an obvious bottleneck, like if I had X and Y, if I've got a set S here with like 4 vertices, and the neighborhood of S, like all of the things that are adjacent to things in S, if that only had 2 vertices, so if I've got S here in the neighborhood of S, well, like there's not going to be any way to match these 4 vertices to those 2 vertices without hitting the same vertex twice, right? So basically, like either you get a perfect matching or you get some really obvious obstruction. Okay, which like generally doesn't always happen in combinatorial problems. It's kind of magic when it does. You can think of König's theorem that way too. Either you get a big matching or there's some obvious obstruction, which is a small vertex cover. Okay. So the next topic we're going to think about is getting a maximum weight perfect matching. So, so here's a problem, which we'll talk about how to solve next time. So let G be a graph. And let W be like some kind of weight function. You've given every edge, you sent it to a real number. And so if we have a subset of the edges, so let's say the weight of that set is just the sum of the weights of the edges in it. So it's like a linear weight function. Okay. So, so here's the problem is to find the matching M of G of maximum weight. Okay. So of course, if you just set all the weights equal to 1 on every edge, that's just saying find the biggest matching. Also, if the weights are positive, like it's kind of clear that you want this matching to be like big. You know, it might as well be the biggest, or okay, maybe not the biggest cardinality, but we're going to kind of be able to deal with like any kind of weight function, I guess. Okay, so we'll talk about that next time.